Okay, so the number that multiplies outside the square root is called the coefficient. We talked about this a bit yesterday. So if I have 2 times the square root of 5, 2 is the coefficient. Square roots with the same radicand, and if we talk about radicands, that's this number here. It can be added or subtracted just the same way you would variables. So you treat like variables. Which means we have to match in order to add them or subtract them. If I have 3 square roots of 5 and 6 square roots of 5 altogether, I have 9 square roots of 5. The square root doesn't change. I can't do anything to it. It's just, if you think you have like little tiles printed with square root of 5 on there, and you have 3 on one part and 6 on another, you have 9 altogether. Okay. And the same thing with subtracting. I do 3 minus 6. So negative 3 square root of 5. So they'll follow all the same rules as our integers did for the adding and subtracting and positives and negatives. It's just that the square root part has to match and it doesn't change. Unlike with multiplication, where when we multiply the square roots together, it did change, but when we're adding and subtracting them, they stay the same. So far, okay? 7 times the square root of 2 plus 5 times the square root of 2 will give me 12 times the square root of 2. 2 square root of 5 minus 6 will give me negative 4 square root of 5. So as long as they match, you just add and subtract the coefficients. It's very nice that way. Sometimes, though, they don't match. Not the way they are. We have to see if we can make them match. Sometimes you can, sometimes you can't. So the first step is to simplify the square root part. Okay. And then, if they match, add or subtract. If not, you've simplified it as far as possible. As long as you've simplified it, you can't do anything else. So you simplify. If they match, you add or subtract them. If they don't, you just stop. Okay, so 20 is 4 times 5, and 5 is 2 times 2. So I have this pair of 2's that I can bring out. That 6 that was already there is still there. Doesn't go anywhere. I bring out the 2, and the 5 gets left behind. So 6 square root of 20 is the same thing as 12 square root of 5. So far, okay? All right, 80 is 2 times 40, which is 2 times 20, which is 2 times 10, which is, hold on, I'm going to go sideways, which is 2 times 5. So I have 2 pairs of 2 that I can bring out. That 4 that was there is still there. I bring out the 2 pairs, 1 each, and the 5 gets left behind. So 4 times the square root of 80 is the same thing as 16 times the square root of 5. Now they match. Now I can add them. So 12 and 16 is 28. I can do the same thing with 75. All right, so 75 is 3 times 25. 25 is 5 times 5. So I bring those 5's out. 3 is still there. I bring out the 5. 12 is 3 times 4. 4 is 2 times 2.
Wait, how come you put 75?
Oh, because I wasn't paying attention. Thank you. Oh, that's too big. Good catch. That should be 3. Okay, here's my pair of 2's I can bring out over here. Times 2, square root of 3. 3 times 5 is 15. 11 times 2 is 22. So I have 15 minus 22, which is going to give me a negative 7 times the square root of 3. If I had, let's say, 2 times the square root of 20 plus 6 times the square root of 75, this is going to end up giving me 4 times the square root of 5 and 30 times the square root of 3. Once I get to this point, 5 and 3 don't match. This is as simplified as it can be, so I stop right there. So simplify them, they don't match, you stop. And that's your answer. Okay. And one of the big illegal things in math is you cannot have radicals in the denominator. Now the ones that we did yesterday where we divided, we were able to divide and then simplify, and they took the radical out of the denominator, and that was okay. Well, this is not a square root. The 6 is. I can't make this into a single fraction because a not square root and a square root don't combine that way. So we have to do what's called rationalizing the denominator. And to rationalize the denominator is a process where you square. Because if we square a square root, it goes away. Now to square this denominator, I need to multiply it by itself. Now I can't just multiply the bottom by the square root of 6, and so I do it to the top as well, because this is the same thing as multiplying by 1, so it doesn't change anything. So you multiply the top and the bottom by the same square root, and what I get is 15 times the square root of 6 over 6. These two square roots cancel each other out, leaving me with the number that was underneath 6. Or if you want to look at it, the square root of 6 times the square root of 6 ends up being the square root of 36, which is just 6. So if you want to multiply them together and then take the square root, you can. Or if you want to remember that when you square a square root, it just cancels the radical and leaves the number. 15 and 6 will both divide by 3, so I reduce those. So my final answer is going to be 5 times the square root of 6 over 2. Okay. If I have a fraction that won't reduce out, like this, I'm going to separate them, which we're allowed to do. Then I'm going to multiply both the top and the bottom by the denominator. I get a 15 up here. I get a 5 down here. Now this 15 and 5 won't reduce because one's inside a square root and one's not. So you can't reduce into a square root from a number that's not in a square root. Because they're not the same, they're not in the same kind of family. So this one is done. We don't do anything else to it. Do you guys want to see a couple more of those? Or, yeah, okay. Let me see if I had a few more. Nope, I didn't. Let me make up some. No, I just did 3/5, didn't I? Yep, I sure did. I'll make up a different one. Okay. So here, 4/3 won't reduce. However, the square root of 4 is a perfect square. So I'm going to go ahead and pull that out. But I can't have this square root of 3 in the bottom. So I'm going to multiply both the top and the bottom by the square root of 3. And square root of 3 times the square root of 3 will give me the 3. Okay. 7 over the square root of 11. Multiply them both by the square root of 11. Nothing will reduce. So that one's done. 8 over the square root of 2, I'm going to multiply by the square root of 2 over the square root of 2. So I'm going to get 8 times the square root of 2 over 2. And 8 over 2 will reduce. And 8 divided by 2 is 4. So we just end up with 4 times the square root of 2. And then 3 over the square root of, or the square root of 3/7. I'm going to split that. And I'm going to get, I put the multiplication, multiply by the square root of 7 over the square root of 7. And even though 21 does divide by 7, we can't reduce this because the 21's under a radical and 7's not. Okay, so we're going to recognize the subsets of the real numbers and recognize the properties of the numbers. So we're going to be able to identify what kind of number we're looking at. They're families. I like to think of families. And we have two major families in numbers. We have real numbers and we have complex numbers. And we're not going to actually deal with complex numbers in this class, but complex numbers are imaginary. And so if we talk about real numbers, we have real family. Complex numbers, not real. Okay? No mosquito worshiping aliens around here. Okay, so maybe that'll help you keep them kind of separate. Before we go into this, though, I want to show you the dolls. The other way you can look at it is with a Venn diagram. So we've got the natural numbers fitting inside of the whole numbers, fitting inside of the integers, fitting inside of the rational numbers. They're all nice and circular. They fit inside each other. And then you've got this rectangle over here. That's part of the real number family, but doesn't quite fit in the nice, pretty, circular. Whoops, what did I do? There, okay. The bold letters at the bottom are how you represent these numbers. If you don't want to write natural numbers, you make a bold N, a bold W, a bold Z, a bold Q for rational. And then irrational is either R minus Q, which is the real numbers minus the rational numbers. That's what you get left. Or you can put a Q with a bar over it, which means not Q. And then R is for real numbers. That's why we can't use R for rational, because R was already taken by real. All right. The flowchart starts this way. Are you real? Okay, if you're real, you're in this box. If you're not, you're over here somewhere. Okay, then if you're real, are you rational or irrational? Rational means that you can be written as a fraction. That's actually what it means. So all the decimals that end to repeat, all the integers, all the fractions. Or you can be irrational, which means you're a decimal that never ends and never repeats. If you're irrational, the flowchart stops there. If you're rational, you can be a non-integer fraction. So you're a fraction or a decimal, or you're an integer. If you're a fraction or a decimal, you stop here. If you're an integer, you could be negative, or you could be a whole number. Whole numbers are 0 through infinity. And if you're a whole number, you can be 0, or you can be 1 through infinity. So this is kind of the flow chart way to look at it. For me personally, I prefer the Venn diagram or the doll, but for somebody, the flow chart might work better. So however it works for you. When we're identifying numbers, this is kind of a nice way to go through to identify, to see what category the number fits in. And then, of course, some numbers fit into more than one category. If you're a whole number, you're also an integer, you're also rational, you're also real. You can go up the flow chart. Everything in the integers is also rational and real. However, if you're an integer, you may not be a whole number because you could be negative. So that's kind of how that flow chart sort of works. And we're going to use that to identify numbers. Now, if you're a square root, the first thing you want to do is see if it'll simplify as a perfect square. 17 does not simplify as a perfect square, so this is non-integer. It's irrational. If I try to calculate it out, I'm going to get a decimal that goes on forever. If it's irrational, it's also real. -2, it's not a counting number because it's negative, so it's not a whole number either, but it is an integer. If it's an integer, it's also rational. If you're rational, you're not irrational, but you are real. Fraction, check to see if it will reduce to a whole number. You know, if it's an improper, it might turn into a whole number. This one doesn't, so it's not any of these categories, but it is rational. That makes it not irrational, so it's real. Decimals are rational if they end or repeat. This one ends. Oh, did I skip 0? Sorry. I totally missed that. Not natural, because we don't start counting with 0. We count with 1. Integer, rational, real. How about this one? That 6 has a bar over it, so it's repeating. Rational or irrational? Irrational, don't repeat. Yeah, don't repeat. Don't end. Okay. Let's just do this, because they're all going to be real. Okay? The only way you get not real is if you have a negative under the square root. We're not going to be dealing with that. So these are all real. Now this one is kind of tricky. I have 0, 5, 0, 0, 5, 0, 0, 0, 5. We can assume that the next one's going to be 0, 0, 0, 0, 5. We're going to keep adding 1 0 every time. Do you think that's rational or irrational? Raise your hand if you think irrational. Raise your hand if you think rational. Raise your hand if you have no clue. Okay, raise your hand if you're not paying attention and you're zombied out. Okay, cool. At least one person's honest. We have a pattern. Irrational numbers have no pattern. Okay, so this doesn't repeat in that it's the same digit repeating every time, but it repeats in that it's got a repeating pattern. Okay, that makes it rational. So if you see a pattern of repetition, and in this case there is a pattern, and it is repeating, it's just repeating, adding a 0 every time, that will still be rational. Yeah, irrational is just, there's no pattern, there's no sense to it, like pi. If you take pi out to hundreds of digits, there's no pattern at all that can be found. And they've had mathematicians have analyzed it, they've had computers analyze it, it's not there. If you see a pattern, go ahead and say it's rational. Because otherwise there's not going to be, it's just going to be a string of random numbers. You'll definitely see that there's no pattern. 18. Well, we can count to 18, right? That makes it natural. If it's natural, it's all of those. Negative 43 over 0. Oops, I lied. I lied. Wasn't paying attention. Can you divide by 0? Okay, so not imaginary does not exist. Not even in the complex number and the imaginary numbers can you divide by 0. You can never divide by 0. It doesn't exist in any family, any number system. So it's nothing, none of the above. Pi, irrational. We have 634 repeating, rational. The square root of 225 is 15. That is perfect square. It is a whole number, but it's also natural number and an integer, and it's rational. 634 that ends is rational. The square root of 4 is 2. The square root of 49 is 7. So this will reduce down, but it reduces down to a fraction. So it's not an integer or a whole number. We go straight to rational. And then negative the square root of 64. The negative is allowed to be on the outside. So we get a negative 8 integer, which makes it rational. Okay. So you guys will want to be able to do that. Look at the numbers and then say we're to talk about properties of exponents. So this is what happens when you multiply exponent numbers and divide them, things like that. We're going to convert from scientific to decimal and from decimal to scientific. We're going to perform computations with scientific notation, and we're going to solve applied problems using scientific notation. A very real world there for scientists. Properties of exponent. We have the product rule. Okay, and what the product rule tells us is if you have exponents with a common base, you add the exponents. So if I have 3 to the 5th times 3 to the 7th, that's going to give me 3 to the 12th. Why that works is because 3 to the 5th is 5 3s. And 3 to the 7th is 7 3s. And if I multiply them together, I count them all up, I have 12 3s. But rather than expand it all out and then count it all up, we have a nice shortcut rule that says just add those together and be done with it. Okay, those two things have to match. So that's what I mean, same base. This is the base. Okay. We have a quotient rule. Okay, or sorry, power rule. Getting ahead of myself. And the power rule says that if you have an exponent and then you raise it to another exponent, you multiply the exponents together. So if I have 3 to the 5th raised to the power of 7, that's going to be 3 to the 35th. And the reason that works, I don't have room. I'm going to put it down here. 3 to the 5th to the 7th is 3 to the 5th times 3 to the 5th. It's 4, 5, 6, 7. Because that's what exponents do, right? It means you multiply that same thing that many times. And then this is 5 threes, 5 more, 5 more, 5 more. So I have 5, 10, 15, 20, 25, 30, 35 threes. But again, we don't want to have to write all this out and then expand that all out and then count up all the threes. So we have that nice shortcut rule that tells us just to multiply those. Now the way you tell the difference between these two, here I have 2 bases, here I have 1 base. So if you have the 2 bases that are the same, add the exponents. If you have 1 base with 2 exponents, multiply them. Okay. And then the opposite of multiplication is division. And the opposite of addition is subtraction. So if we add exponents when we multiply, we subtract exponents when we divide. Again, same base, very important. M minus n, and I'm going to flip those over. I have 1, 2, 3, 4. Well, I'm not going to fit that there. Hold on. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And here's why that works, because 3 over 3 divides out and makes a 1. This is a 1, that's a 1, here's a 1, and that's a 1. How many 3's do I have left over? 2. 7 minus 5 is 2. So again, this spares us having to expand it all out, cancel all the matching ones that, 3 divided by 3 make a 1, and this 3 divides by that 3 to make another 1, and so on and so forth. You just go ahead and subtract them. Save lots of time and paper. I'm going to do some of these 2 bases being multiplied together, so I'm going to add the exponents. Okay. If I have 2 y's, I have 2 z's. I'm going to add the exponents on the y's, and I'm going to add the exponents on the z's. So y goes with y and z goes with z. So 5 plus 9 is 14, and 2 plus 4 is 6. And this one I have x goes with x, y goes with y, z's a loner. 2 plus 13 is 15. 3 plus 9 is 12, and z doesn't change because we didn't multiply it by anything. So far okay? Here I have 1 base, 2 exponents, so I multiply those together. Here I have 2 bases, but they don't match. So what I do is I multiply both of these exponents, kind of like distribution in what we were doing before. So 5 times 4 is 20, and 5 times 3 is 15. Oh, hold on. I'll go back. So I do 9 minus 4. So I'll just write that out. Here. And then this one I do 10 minus 3 and 7 minus 3. So I get x to the 7th, y to the 4th. I have x's and y's and then this loner z. So I just subtract those, but that z doesn't have anything, so it just sits there. So I get x squared y to the 6th over z to the 2. That stays where it was because we didn't change it. So it just hangs out where it was. Okay, now this one combines. I have multiplication here in the center. It kind of looks like that's a multiplication sign. So I'm going to multiply across the top, and then I'm going to multiply across the bottom. Then I'm going to simplify by division. So the x doesn't change. If there's no exponent, it's a 1. So I have 1 plus 3, which gives me 4. And then the z didn't change. And here, nothing really changes because there's no comments. But I'm just going to put it in order, alphabetical, because I like it better that way. Then I'm going to divide. I'm going to do 5 minus 2, 4 minus 2, 8 minus 4. Now, you know when we were dealing with regular fractions, we could cross cancel first. You can cross cancel these first also if you want to, and then multiply them together. So I'm going to rewrite that up here. Okay. Oh, I forgot the x squared. So 2 goes into 5 3 times. That makes this x go away. 4 goes into 8 4 times, and that made that go away. And here I have a y over a y. 2 goes into 3. And I just divided. I meant to subtract. Guys, catch me when I'm doing the wrong math. Oh, wait, you can't. I'm teaching this to you. Sorry. Pretend I didn't do that, and let's start over. I think I did the right. No, I didn't. Okay. There's 4 z's and 8 z's, so this leaves me with 4 z's. 8 minus 4 is 4. There's 2 x's and 5 x's. 5 minus 2 is 3. 3 y's and 2 y's. That leaves me with 1. And then there was 1 there because there was nothing on it. So all of the ones in the bottom have been canceled out. So what I have left is I have 3 x's, 1, 2 y's, and then 4 z's. So if you want to cross cancel, you can, or you can do it this way and multiply it all together and then simplify it. Either way, you're going to get the same answer. It's just a matter of which way makes the most sense and works the best for you. Okay? If you have a 0 for an exponent, your answer is 1. Always 1. The reason it works is because if I have x squared divided by x squared, if I divide anything by itself, it's 1, right? 2 minus 2 is 0. So anything to the power of 0 equals 1. So 7 to the 0, 1. Pi to the 0, 1. Negative 5 to the 0, 1. If the negative's in parentheses. If the negative's outside of the parentheses, it still hangs out because the 0 is not touching it. So negative 1. So 1 billion raised to the power of 0 equals 1. Infinity, 1. See how easy? You never have to actually calculate anything on these. You go, oh, 0 exponent's just 1. So those are nice. Negative exponent rule. Okay, basically, negative exponents are illegal, except for scientific notation. That's the only exception. No negative exponents. So since they're illegal, they're bad, and we shove them in the basement. Okay, so 8 to the negative 2. Negative 2 is bad, so I shove it downstairs. And then I make it positive. 5 to the negative 3, not allowed. 7 to the negative 1, that's going to be 7 to a positive 1, which is just 7. So this would be equivalent to 1 over 64. This would be equivalent to 1 over 125, and this would be just 1/7. But anytime you see a negative exponent, if it's on a regular number, you just shove it in the basement and put a 1 over top of it. Okay. If I do division and my exponent on the bottom is bigger, this is the same as x to the 4 minus 9, which is the same thing as x to the negative 5, which is not allowed. 1 over x to the 5th. So you can go this route, or you can do it kind of like a tug of war. You're going to subtract. 10 is bigger than 3. So 10 would win the tug of war. So the difference is 7, and that'll stay on top. Excuse me. 13 is bigger than 7, so that 13 would win a tug of war, and it would pull it down to the bottom. So when I do 13 minus 7, I'm going to get 6, and it's going to stay on the bottom. So you can go the negative exponent route and then correct it, or you can subtract the numbers, and then whichever one is bigger, that's what side you stay on, like you want a tug of war. The 12 is going to win, right? So I've got an 8 on the bottom. The 5 is going to win, so I have a 3 on the bottom. The 7 is going to win, so I have a 2 on the bottom. When that happens, I can't have nothing up top, so put a 1. And here's one of those we multiply first, or cross cancel and then multiply. I'm going to multiply first. I have x to the 5th. 1 and 3 is 4. And then 10 z's. And then nothing here. Y times y to the 3rd adds the exponents. Yeah. So the 12 is going to win between the 5 and the 12. The 15 is going to win here. And then the 10 is going to win here. So when you multiply, you add. When you divide, you subtract. And if your bigger one is on the bottom, it carries all the weight and pulls it down. Or, again, like I said, you can do the subtraction and have the negative and then fix it by putting it down in the denominator. If I have 10 to any exponent, that's just telling me how many zeros I have. So I don't have to multiply out 10 times 10 times 10 times 10 9 times. I just write a 1 and put that many zeros. So that's nice. If I have a negative exponent, that tells me how many decimal places I have with a 10. So if I have this 10 to the negative 9, I have 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then my 1 to make 9 decimal places. Okay, so if the exponent's positive, number of zeros. If the next exponent's negative, number of decimal places. Okay. Any questions on those two things? This is here the basis of scientific notation. if you're in the field of, let's say, astrophysics, and you're calculating mass of planets and distance between galaxies and even distance between planets in our own solar system, these are huge numbers, right? I mean, they're very large, billions and billions and billions of light years. These numbers are not easy to work with, you know. If you are a engineer working with nanoparticles, you're talking about microscopic computer parts, and you want to do calculations for that. You're talking about decimals that are 0.00, like all these zeros in like a 651, and you have to do calculations. These are not easy numbers to calculate with. Any kind of number that's very long, either a long giant number or a long microscopic number, decimal, they're very difficult to work with. So what happened is that they used that power of 10 we just talked about. They round. You know, it's not exact numbers, but it's, you round, you use a power of 10, you shorten the number. It makes calculating with these giant long numbers easier. And so that's really what scientific notation is. It's just a shortcut for writing really long numbers. And this can be a large whole number or integer, or a long, which means tiny, decimal. Okay? And they're in the format of a number, a decimal, 2 more decimal places, times 10 to a power. Okay. This exponent, I'm just going to put an E for exponent here. If it's positive, we're talking about a giant number. A long number. Big. If it's negative, we're talking about a long decimal. You know, like 1/100 trillionth of an inch or something. You know, just like lots of zeros before you get to any numbers. So if we go from scientific to decimal, what I'm going to do is I start with my 2 and my 6. This tells me the number of places I have to move. So here's where my decimal was. So I go 1, 2, 3, 4, 5, 6, 7. That's how many places I move the decimal. And any blank spots get filled with zeros. So this is actually going to be that number. What's that? 26 million. Shorter. Okay. If I have a negative exponent, I start over on this side, and I've got 4 decimal places to move. So 1, 2, 3, 4. I put the decimal here, and I fill these with zeros. So this is 0.00011. A positive exponent tells me to move to the right. And it tells me how many spaces to move. And I'm moving that decimal point. A negative tells me to move to the left. So the same kind of idea as on a number line, positives move to the right, negatives move to the left. So we're not changing that in any way. Any questions?